Hello everyone and welcome back to this next lecture. So this is where we had left off in the previous lecture where we had compiled the driver.lib project. So with this now we have both projects compiled and ready to be executed. So for this first I will bring the microcontroller into the video. So you can now see the microcontroller in the video. There is no change in the connections with respect to the previous example. So this is basically the same full bridge converter. So we are talking about the same PWM connections and therefore the same connections to the solderless breadboard. So this way I can directly zoom into the oscilloscope and we can now enter the debug mode. So for now, channel 1 of the oscilloscope is connected to S1 of CPU 1 and channel 2 is connected to S2 of CPU 2. So with this, I'm now going to go into the debug mode with CPU 1. And the program is ready to be executed. So I'm going to select the CPU and click on continue. So you will now see a very interesting waveform, and the reason for this is that we have the same time setting as we did for observing the 5 kilohertz and 10 kilohertz waveforms. We now have a 50 hertz waveform. So I'm going to come here and change the time setting. So I'm going to increase it. So now we are at a 5 millisecond time period, which means each rectangular waveform has an on time and an off time of 10 milliseconds. So this clearly shows that because I have chosen 50 Hz to be the frequency of the phase angle and therefore of the modulation signal, our S1 and S2 are now operating at 50 Hz frequency. So which means that S1 remains on for the entire positive half cycle of the modulation signal and S2 remains on for the entire negative half cycle of the modulation signal. So at this point of time, let me go and connect one of them to S3. So you get, of course, it seems like a rectangular sinusoidal waveform, but this is actually incorrect. This is mainly because this oscilloscope doesn't have the resolution for this. So I will have to decrease it further. And you see now that we have this, it is gone. So again, this is actually very difficult to observe for the simple reason that we now have 150 Hz waveform and the other to be a 5 kilohertz waveform. So what I will do is I will switch over the two channels. So now channel 1 will measure the gate signals at S3 and channel 2 will measure the gate signals at S1. The reason is because channel 1 is where the trigger has been enabled, and now you can clearly see that the gate signals at S3 are now changing in a somewhat, let me just increase this, and now you can see fairly clearly that the gate signals at S3 are following a high frequency sinusoidal pattern, right? So we saw it before. So you can actually even remove this and check, and you can see now it is uninterfered, and you can see how it is increasing from an absolute maximum to an absolute minimum. That is the pulse width. So this shows that we now have achieved a certain level of unipolar modulation method. So now let me just one last check I can do is to just check if S3 and S4 are indeed 5 kilohertz waveforms, and in this case now you can see yes they are. This is very much the same result that we got in the previous section, where or rather the previous simulation, previous experiment with the bipolar PWM, and this is what we're getting here as well. So these are the gate signals of S3 and S4, and here you can see that they are indeed, this is indeed following a sinusoidal pattern, right? So with this done, I can now go over and try to connect CPU to, and with this I can go and load the program. So with this running, I can now switch it over to the EPWM4 and EPWM5 that are connected to CPU2. So first I will connect, as usual, the channel 1 to EPWM4A, which is the gate signal to S1, and the channel 2 to EPWM4B, which is the gate signal to S2. So let me again increase this, and this will show that they are again 50 Hz rectangular waveforms. So which means S1 and S2 of CPU2, which are EPWM4A and EPWM4B, are also switched at 50 Hz frequency, which means they will stay on, or rather S1 will be on whenever the modulation signal is in the positive half cycle, and S2 will be switched on whenever the modulation signal is in the negative half cycle. So with this done, I am now going to go over. I will switch S1, the channel 1 to S3, and I'm going to decrease this. And you can see that we are now getting a similar sinusoidal wave, or rather shape, that we got before. So I'm now going to connect this one as well, and you can now see that the blue waveform is connected to S1, and this is at a much lower frequency than before. So this shows how S1 and S2 are operating at 50 Hz, while S2 and S3 and S4 are operating at 5 kHz. And just for the sake of one last comparison, let me connect this to S4. And now you will see both S3 and S4 are connected to the channel oscilloscope channels, and you can see this is exactly the same result we saw in the previous experiment as well with bipolar PWM. So which means that S3 and S4 are operating almost in a bipolar manner, whereas S1 and S2 are now operating at a low frequency, and this is what enables us to achieve unipolar modulation, because S1 and S2 remain on for the entire positive or negative half cycle of the modulation index, and therefore that results in either a plus VDC during the positive half cycle or a 0, and in the negative half cycle with minus VDC or 0. So I hope you got exactly the same results. With this, I am ending the microcontroller video, and we are also at the end of this lecture. So the idea behind this lecture was to show how we can achieve unipolar modulation. Now again, like I said, there are several ways of actually implementing unipolar modulation, and I myself have used maybe 2 or 3 methods of doing so. I just found this to be the most convenient, because in this case you don't have to actually keep changing your action qualifier control registers, and also more or less this also opens up the possibility of another algorithm where you might want to switch S1 and S2 operating at higher frequencies and S3 and S4 operating at 50 Hz frequencies every now and then. So this will kind of even out the switching stresses among all the power modules, because at the moment most of the switching losses are occurring in S3 and S4, while S1 and S2 have very low switching losses. So with this, I will bring this lecture to an end. Now that we have completed both unipolar and bipolar modulation with the full bridge converter, the last method which we are going to examine with this full bridge converter is going to be the phase shift PWM, and that will come in the next lecture. So if any of this did not work for you, or you have any other doubts, or you ran into any other issues, please post in the Q&A forum and I'll be happy to help you. Otherwise, I will see you in the next lecture. Thank you so much for listening, and see you soon. Goodbye for now.